Welcome back to our Chapter 5 material on acid-base chemistry in the context of equilibria. Previously, we introduced our acid-base definitions and a couple of quick pH calculations. In this video, we're going to define strong and weak acids and bases. We're going to quantitatively deal with these weak and strong acids, weak and strong bases, and conceptually predict which ones might be stronger than others. All right, so we can classify our acids as either strong or weak, and we can classify our bases as either strong or weak. This classification is going to be a way to describe the extent to which our acids or bases react when they're in our solution. If we have a strong acid, these are going to react completely. If we have a weak acid, this is not going to react completely and instead is going to reach some equilibrium with a mixture of reactants and products. We can look at this using our equilibrium expression. If we have an acid in water, it will react and maybe reach some equilibrium if it's a weak acid. This equilibrium position is described by our equilibrium constant. For this reaction, we'll call it Ka. As we said, for our strong acids, these are going to be acids that react completely with water, that react and form almost entirely products, H3O+, and whatever our conjugate base might be. Like we said, we can look at this generic reaction. HA can be some generic acid producing A-, its conjugate base. If you put HA in water and it's a strong acid, what we end up with is 100% products. None of our starting acid molecule is remaining behind. Quantitatively, our Ka value is going to be something that has lots and lots of products. It's going to be a numerical value, something bigger than 1. As it turns out, there are only a handful of acids that are strong. There are 6 on this slide. I believe there's maybe just one more besides these. It's a good idea to memorize these 6 strong acids. Hydrochloric, hydrobromic, hydroiodic acid, right? The halogens apart from fluorine form strong acids. Perchloric, nitric, and sulfuric acid. We can visualize this graphically, right? How much of our reactants and products do we have at equilibrium? Well, here are those 2 products. We have none of our reactant left behind. Or zooming in on our test tube, we only have the conjugate base and H3O+ present. The alternative is a weak acid. Weak acids only partially react with water. In fact, most of the time, we're going to have only a tiny fraction of our weak acid molecules react to form the products. We're going to have our generic acid reach an equilibrium position where we might end up with some of our products, but mostly still our starting reactants present in our test tube. Numerically, Ka is going to be a small fraction, less than 1, which means, we have more reactants than products. We can visualize this. HF, this was our starting weak acid, hydrofluoric acid. In our test tube at equilibrium, we can count them up, 6 hydrofluoric acid molecules. Our 7th hydrofluoric acid molecule has dissociated into F- and H3O+. This is maybe even a bigger exaggeration than it looks like. Graphically, we can picture this. Okay, we have a majority of hydrofluoric acid molecules still present. Only a tiny fraction of them have produced that conjugate base and that H3O+. It's probably not even going to be 1 in 7 ionizing to form products. It's probably going to be closer to maybe 1 in 100 or 1 in 1,000 or 1 in 1,000,000 reacting to form these products, depending on the magnitude of this Ka value. Since our weak acids reach some equilibrium position, we can solve for the concentration of our weak acids at equilibrium using our regular equilibrium techniques. We can use our ice table to figure out what our equilibrium concentrations should be. And we can use our K expression to solve for that, maybe numerically. Our practice problem says find the pH of a 0.600 molar solution of benzoic acid, where we know the Ka value for benzoic acid. Let's set up our ice table. 0.600 molar of our starting molecule. We can assume that we have none of our products to start with. The concentration of water does not matter because it's a liquid and it won't appear in our Ka expression. Filling in this ice table. We're going to do this reaction X number of times. Keep track of our coefficients. Turns out they're all ones here, so we're relatively safe. And we can add those first two rows to equal our equilibrium row, which now contains some value for X. Our last step is to write our K expression and fill in our equilibrium concentrations into that K expression and solve for X. We have two options at this point. We can do some algebra and solve using the quadratic formula. Or alternatively, since our K value is very small, we expect this reaction to not happen very much. We can try to use that small x approximation, make our lives a little bit easier. I'll leave the algebra to you if you want to figure it out. Our answer should be x is 0.00624, and therefore the pH is going to be negative log of our concentration of H3O+. Well, H3O+ is just X. pH has to be 2.204. There we go. Weak acids only partially react, which means they will reach some equilibrium. Turns out we already know how to deal with equilibrium from our previous ice table strategies. We can have analogous definitions for strong and weak bases. Strong bases will also react completely. They'll produce 100% products. If we have a Bronsted-Lowry base reaction, here we have some generic base, its generic conjugate acid, and some hydroxide. Okay, we can have this equilibrium constant known as Kb for our Bronsted-Lowry base reaction. Strong bases will have a Kb value much, much bigger than 1. Well, in reality, there are only a handful of strong bases, and actually these are going to be ionic compounds that dissociate to produce hydroxides. These are more the Arrhenius style bases, where they just dissolve completely because the positive counterion here is completely soluble. We have our similar strategy for weak bases. Weak bases, okay, here's a generic weak base, again reacting with water to produce its conjugate acid and hydroxide. For weak bases, these only partially react, and they reach some equilibrium where we have the Kb value some tiny fraction less than 1, which means the amount of original base is much larger than the amount of products that get to form. Once again, most of our bases are going to be weak, and if it's not one of those common strong bases, we can assume that we have a weak base. If we want to deal with our weak bases quantitatively, well, good news again, we can go back to our ice calculations. The magnitude of Kb dictates where our equilibrium position will lie, and we can do our ice calculation to solve numerically what that value is. So for example, trying to find the pH of a 0.25 molar solution of ethylamine. You know the Kb value. This Kb refers to our base reacting with water, producing hydroxide and that conjugate acid. We know the initial concentrations, 0.25 molar and none of our products. Again, we can ignore water since it's liquid and won't appear in that K expression. Now it's just a matter of solving for this ice table. Let's say we do this reaction X number of times. Our equilibrium concentrations, therefore, have to be this. We can use these concentrations in our K expression. We know Kb, we can set up an equation and solve. Again, we have two options. You can do some algebra and the quadratic formula, or we can try to do the small x approximation. Since our Kb value is very small, we're only going to do this reaction a handful of times. X is also going to be small, make the algebra a little bit easier. We get our value of x is 0.0118, which also corresponds to our concentration of hydroxide. To find the pH, well, multiple strategies exist. Find the pOH to find the pH, or find the concentration of hydronium to find the pH. Regardless, we should end up with some answer. pH is 12.07. If we want another way to quantify how acidic or how basic our solution might be, we can introduce this idea of percent ionization. Percent ionization is this metric: how much product did you form compared to the initial concentration of your reactant in your solution. Multiply by 100 to frame it as a percentage. Great. What percentage of your initial acid molecules reacted to form H+? Or what percentage of your initial base molecules reacted to form conjugate acid? The way we solve this, well, again, it's an ICE table calculation. If we scroll back a second to figure out the percent ionization for our base here, we can compare the initial concentration of our base to the final concentration of our conjugate acid. Or similarly to the final concentration of hydroxide. Essentially, we're comparing in the ICE table X to our initial concentration for the reactant. This was our example on the previous slide. We can take our X divided by our initial concentration, multiply it by 100, and we end up with 4.72%. This gives us some intuition, right? Our Kb value was very small. We expected a mixture of reactants and products, and maybe more reactants remaining than products at equilibrium. Well, for this particular solution of ethylamine, only 4.72% of our starting molecules were able to react and form those products. Very cool. All right, we've done some calculations with strong acids, with weak acids, with strong bases, with weak bases. If we want, we can also try to build our intuition and compare which acids do we expect to be stronger? Which acids do we expect to be weaker? Well, we have a couple of metrics. We can use our K values. Ka and Kb will tell how strong or weak each individual acid or base might be. Smaller values on that equilibrium constant indicate that we have a weaker acid or base. We can also use pKa or pKb. This P is the same as we use for pH. Just take the negative log of your Ka or the negative log of your Kb. Right? Change your K values, which can range from wide orders of magnitude, switch them to this log scale so that they range from numbers about 0 to about 14. Since we have this negative sign, our pK values will be smaller when we have stronger acids for pKa or stronger bases for pKb. For a conjugate acid-base pair, we can also introduce some equations. Numerically, a Ka value times the Kb value for a conjugate acid-base pair have to multiply together to equal exactly Kw. Or in terms of pKa's and pKb's, when you have a conjugate acid-base pair, the pKa of your acid and the pKb of its conjugate base have to sum to exactly 14. If you're looking to understand where these equations come from, well, write out the equation for Ka, write out the equation for Kb. You can see that those multiply together to equal exactly just our Kw equation. What this tells us is that our conjugate acid-base pairs, they're going to kind of complement each other. They're going to be inversely related. within a conjugate acid-base pair, if you have a relatively strong conjugate acid, its conjugate base will be relatively weak. Or vice versa, if you have a very, very weak conjugate base, the conjugate acid is going to be much, much stronger. We can see some examples, right? Hydrofluoric acid. This is a weak acid. Its Ka value is 10 to the negative 4. So it's a weak acid, but it's on the stronger end. Its conjugate base is fluoride. Fluoride has a Kb value of 10 to the negative 10. Very, very, very weak base. Or if we slide down the other way, ammonia has a Kb value of 10 to the negative 4. It's a weak base, but in terms of weak bases, it's among the stronger weak bases. Ammonia's conjugate acid is ammonium, NH4+. This is going to be a very, very weak acid. Or we can slide even further. Water is an extremely weak acid. Its conjugate base is hydroxide. Hydroxide is a strong base. The conjugate of a strong base is going to be an extremely weak acid. Or vice versa, if we have a strong acid, hydronium is the strongest acid here. If we have the strongest acid, its conjugate base is going to be an extremely weak base. So once again, we're going to have this inverse relationship within a conjugate acid-base pair. Take a second to see if we can attack this practice problem. We want to examine the stronger acid, HNO2. We can see that this has a Ka value of 4 times 10 to the negative 4. HCO2H has a Ka value of 1.8 times 10 to the negative 4. Which of these values is bigger? The bigger the value of Ka, the more products we'll have form, the stronger our acid. Nitrous acid here is going to be slightly stronger. For our base question, we can think about NO2 minus or CO2H minus. A few ways we could think about this. We could try to numerically calculate Kb's and compare those Kb's. Or we can just think about the trends. NO2 minus is the conjugate base of HNO2. CO2H minus is the conjugate base of HCO2H. If this acid is stronger than this acid, its conjugate base will be weaker than the other conjugate base. So qualitatively, we can just look at our K values, decide which one is bigger. That helps us decide the stronger acid. For the stronger bases, maybe we have Kb values and we can compare. Or maybe we can think about the opposite trend for the Ka of each's conjugate acid. One last thing. We'd also like to be able to predict our acid strengths or our base strengths based on chemical structures and based on maybe some periodic trends. If we're just looking at a chemical formula and we forgot our table of Ka and Kb values at home, can we still predict which acid might be stronger? Well, okay, there's going to be a few trends and a few different classes of molecules that we can consider. We can start with binary acids. Binary acids have hydrogen bonded to just a single atom. Our acid will be stronger when that bond between hydrogen and our other ion is easier to break. Our bond strength, we need to think about two trends. Within a period, our bond strength is going to be related to electronegativity. The more electronegative our other atom is, the easier it is to break that HX bond. More polar bonds are easier to break. And so as we go right on the periodic table, there's a greater difference in electronegativity between our HX bond. It's easier to break and our molecules become more acidic. Maybe we already have this intuition a little bit, right? If we're comparing H2O and HF. HF is going to be a weak acid, but it's among the stronger of our weak acids. We have a Ka value approximately 10 to the negative 4. Water, on the other hand, is our weakest acid. This is very, very weak. Moving from oxygen to fluorine, we've changed our electronegativity difference, and we've drastically changed the strength of that HX bond. The other trend that we need to consider, if we're looking up and down on the periodic table among a group, instead of electronegativity, the trend that is most important is going to be bond length. The longer our bonds, the easier it is to break. As we go down the periodic table, our elements get much bigger, and therefore those HX bonds are easier to break, and our molecules become more acidic. Within the halogen group, HF is a weak acid. HCl, maybe we've memorized this. This is going to be a strong acid. Just going one period down, we've gone from a weak acid to a strong acid. Right? So maybe we already had this intuition, but now we have an explanation for why. Here are those results. Left to right, we need to compare electronegativities. Up and down, we need to compare atomic radii, at least for our binary acids, where hydrogen is directly attached to just a single other atom. The other class of acids to consider are oxyacids. Here we have our hydrogen attached to oxygen always. Those oxygens are then attached to some central atom. Once again, we're thinking about stronger acids having this OH bond that's easier to break. Again, we need to consider two trends. If we're comparing two oxyacids with the same number of oxygens, then the trend that is most important is going to be the electronegativity of our central atom. The more electronegative our central atom, the more the electrons are drawn away from that oxygen, the more the electrons are therefore drawn away from that hydrogen. There's kind of a cascading effect here. The stronger our YO bond, the weaker our OH bond, the stronger our acid is. So the more electronegative our center, the stronger this acid becomes. Comparing this IOH bond with this BROH bond, bromine is going to be a more electronegative center. We expect this bromine containing acid to be stronger than this iodine containing acid. The other way that we can compare oxyacids, maybe we have the same central atom, but we have different numbers of oxygens. Sulfuric acid versus sulfurous acid, or nitric acid compared to nitrous acid. Right? Sometimes we have two related oxyacids, but different number of oxygens. The number of oxygens surrounding our central atom will change the oxidation state of our central atom. The larger that oxidation state of our central atom, the more electrons are pulled away from these oxygens, the more electrons are pulled away from those hydrogens, the weaker that OH bond. So comparing oxyacids with the same central atom but different numbers of oxygens, we can think about the oxidation state. Alternatively, we can consider our conjugate bases. The more stable our conjugate base, the more acidic our acid can be. Well, the more oxygens that we have, the more resonance that our conjugate base can exhibit. And more resonance stabilizes our conjugate base. So another way of thinking about this, when we have more oxygens, we have more resonance in that conjugate base, stabilizing that conjugate base, making our acid a little bit stronger. An example maybe we already have some intuition about, H2SO4 compared to H2SO3. Which of these is stronger? Well, what do we know? We know that this is actually a strong acid. Sulfuric acid is one of those 6 or 7 strong acids. Sulfurous acid is going to be weak. It's not one of our strong acids. Maybe we already have this knowledge. Now we have some intuition for why that's the case. The oxidation state on the sulfur in sulfuric acid is much bigger. Well, in fact, exactly 2 bigger. The oxidation state for sulfur in sulfurous acid is smaller. The larger our oxidation state, the stronger our acid. We'll end here with a couple of practice problems. Pause here, see if we can get the right answer, understand which trend we need to examine, and I'll try to highlight the answers in a moment. H2S and water, we need to think about the size of our atoms. The bigger the atom, the more acidic it can be. Hydrosulfuric acid is going to be stronger than water. In B, we have bromic acid compared to bromous acid. These are oxyacids. We need to think about, well, oxyacids with different numbers of oxygens compare the oxidation states of our central atom. A larger oxidation state on the left means that HBrO3 is going to be a stronger acid. For question C, we have HClO, NaOH. Here we have a different central atom in this oxyacid kind of scheme. If we change the central atom, we need to compare our electronegativities. The more electronegative our central atom, the stronger that bond between oxygen and the center atom, the weaker the bond between oxygen and hydrogen. Chlorine is much more electronegative than sodium, and so it's going to be a stronger acid. Note here, this is what we expect anyways. HClO is going to be one of our weak acids, and sodium hydroxide is not an acid at all. In fact, that bond between sodium and oxygen is much weaker than the bond between oxygen and hydrogen. We'd rather break that sodium-oxygen bond than that oxygen-hydrogen bond. Right? Sodium hydroxide is one of our strong bases. All right, that will wrap us up here. We've introduced strong and weak acids, strong and weak bases. We can do some numerical calculations. We can have some intuition about what acids and bases might be stronger, whether we know the Ka values and Kb values, or whether we just know our chemical structures. I hope this has been helpful. Please let me know if you have any questions. I look forward to seeing you in the next video.